Okay, so this lecture is pre-recorded for next Monday, October 9th, because Monday and Wednesday I will be outside of the campus for several invited talk in the conference. So I pre-recorded this lecture and also next lecture, so all of you can watch the video during our class time. Okay, so let's get started. Now, all the logistics are the same, except one thing. Here, for the midterm exam number 2, in previous lecture, we talked about the format, and also I uploaded some examples, excellent examples in the Canvas, so you can look into that. Now, you can, before you make decision of which topic you will work on for the midterm exam number 2, please talk to me first. Both you and your group members, okay? Either individually or collaboratively, talk to me first. And then I can help you to refine the project. Then you can work deeper into the topic and then prepare presentation accordingly. We have about 1 month, a little bit less than 1 month. So we have sufficient time for all of us to dig into the topics you have interest. Okay, so make sure, let me know, email me, and we can discuss either through the email, and you give me some background first, and then we can discuss through the email, or we can schedule a Zoom meeting to talk individually. Okay, I hope all of you will benefit from this presentation and also the final report. Okay, so that's all for all the logistics, and let's start today's lecture. So in last lecture, we talked about the final distribution of many steps, many individual steps summing together, right? So, and we said that this distribution actually is the final distribution is a Gaussian distribution. It's a normal distribution, right? So today we will get deeper about this. Firstly, we will talk about the special example that is from a binomial distribution. So we know what is binomial distribution. That is the flipping the coin, right? So we can let's see how the binomial distribution transition to the Gaussian distribution. And then after that, we will show one mathematical derivation about the principle we discussed, and then see how that mathematically correct, okay? By convolute many steps together, then we can get a final Gaussian distribution, okay? So first, let's look at the binomial distribution, how that it transitions to the Gaussian distribution. So what is binomial distribution? So binomial distribution actually, one type of binomial distribution actually is the toss a die, right? Toss a die for many times. So we know every die has multiple surfaces. So when you toss it for n times, you will have many different outcomes. Those outcomes actually follow the probability theory. For example, the probability after the n times tossing of a die, the probability of having k times the designed side facing up, that if that probability is called n, it's called p, okay, called p, then that probability can be described by an equation, okay? So this die, we know die has 6 faces, and then if there is one face is designed, and then we want to if we want to know after n times of toss, if we want to get k times with that designed face up, now what's the probability? That probability, if we call p, and then we call it p, and then this is small p, different. The small p and the big p is different. Small p is actually the for each time for that face, that desired face to be desired side to be face up for one time. What's the probability? Okay, if you have 6 face and each face is they have the same probability, okay, they are equal, then 6 face, then small p equals to 1/6, right? 1/6. So, and then capital P actually is the final probability that we have this one face that has a 1/6 probability shows up for k times after n times of tossing. Okay, so then that final probability actually equal to nk times p to the power k, 1 minus p times n minus k power, right? So this nk in the parentheses, this actually equals to n factorial. We know what is n factorial is: n times n minus 1 times n minus 2 times n minus 3 all the way up to 1, right? N factorial divided by k factorial and divided by n minus k factorial. So we have learned the combination and sequence before. What does this mean? This means it's a combination without a sequence, right? So n minus 1, the n factorial actually tells us all the sequence. And then within that sequence, you have 2 groups. One is k, the rest is n minus k. The sequence among them doesn't matter, right? So this exactly is the problem of the dice tossing problem. We don't care at which time we get that desired face up. We just want to know. We just care overall among n times. We want to get k times with desired side face up. What's the final probability p, right? So this actually help us to get the combination instead of sequence, right? And then among that, you have k times desired side up. So each time is the probability small p. So then we have p to the power k. So kp multiplied together, and then the rest of the probability actually is 1 minus p. So all the rest sides, right, 1 minus p, and then they will get n minus k times, right? So 1 minus p times nk times for time multiplied together for n minus k times. Right? So this p, final p, actually is the final probability satisfy this condition. And when we change k, change n, change p, this probability follow a binomial distribution. Here, often people replace 1 minus p as q, and p and q added together equal to 1. 100% means all the faces counted together. Okay, so usually people use p and q, but anyway, you actually only have two things important. One is p, one is q, right? This p and q, this determines the final result. You got n and k. That's what you already defined. That's what we want, right? P and q determines that how big is the p. Larger p, then you get a larger this probability, right? Now this is we toss a die, right? Toss a die. Now, and if as I write here, so for the side, for example, for the side one dot here, one side up, then the probability is 1/6, right? And then if we following this condition, we get this probability distribution. And then here, this nk, this value is called a binomial coefficient, always called binomial coefficient. Okay. Now for this probability, this actually is a distribution, right? This is a distribution. Now for this distribution, we can actually find that it is normalized, because we want to know k. We want to know which, when we do this experiment, when we toss n times, we want to know what is the value, what is the value of the k that is the largest. K can be many value, right? K can be many. Or if we don't have any chance has this surface up, then it's zero times. What is probability of 0 times? and if this k changes, at which value it gives the largest probability. The distribution it can have many value, but the largest value tells us when we toss this dice, there's very likely that a value will appear when you do it. Okay, so that's the meaning of the probability distribution. Right? So now, if we look at this distribution further, we will find that let the p and q, p plus q equal to 1, and then we will find that this distribution actually is normalized. So as the k change from 0 to n, right? So 0 means there are no chance that the desired side is up. N means when we toss the dice, all the face, every time we do, that desired face is up, right? Of course, 0 and n both are very rare, very rare. The maximal chance is in between them, right? So then, if we add all these chances together, we will get the final probability as 100%, right? 100%. So it means that anyway, there's one time, there's one chance, right? Now, this distribution also we can calculate their important parameter, especially the mean and variance, as we did before, right? So if we calculate the mean, then we use the k inside, k average, right? So k is the k value in, and then times this probability. Because here we toss the die, it's not in a continuous way. Every time you toss, it's like a discrete event. So then we actually add things together. So k times the distribution, and then different k, different p added together. Okay. So then you k, and then p, you have the value here. P is this value, k is this value, and then summing together. You can practice it. When you do this, you will get the value NP. Okay. So this is the mean value of the k. Okay. So means that distribution, the middle value is actually NP. Okay. And then we can also calculate the second moment. So k square means k square average. Second moment, the k square, put it as k square here, times the distribution, and then summing together. That value actually equal to NP square plus NPQ. So the k square. Then the variance actually is the k square minus k square average minus k average square, right? We know that is the variance. Then is the NP square plus NPQ minus NP square. So NP square cancel out. Then we will get NPQ. So the variance actually equal to NPQ. Okay. So this actually is very useful results. So you can calculate them, also all of them by yourself and see. Now, if we have this value, this we already know. If we increase the time of the event, that means we increase n, right? Increase n. Now, if we have n equal to 6, we do it only 6 times. Then, if you use this equation, you check it. If it's 6 times, then this p at each time you have a value. You can plot it. The p value n equal to 6. K varies from 0 to 6. Right? K from 0 to 6. K is the time that we get that desired side facing up. So we have K change from 0 to 6. And then you will find that the value actually, the distribution looks like this. Okay. And then the mean value is called NP, right? N equal to 6. P is 1 over 6. Then mean equal to 1. What does that mean? That means that if we have this dice, we toss it 6 times, and each face, and the desired face, and the one dot face up is 1 over 6 by itself. But if we do 6 times, we will have 1 time. We will very likely we will have 1 time that have that face up. Okay, only one time, right? So that's very reasonable, right? We only each time we most likely is every face show up one time, right? Now that's 6 times. If we do many times, we increase that number. We increase to 100 times. Then n increased to 100. Other value remain the same. Okay. Then we put a k. Now k will vary from 0 to 100. So then you plot this. You can add the value in. Now you will find the value actually looks like Gaussian. Looks like the Gaussian distribution now. Looks like the normal distribution now, right? So, and then the mean is NP, right? Is 100 minus 100 divided by 6, right? So you add 100 times, and then each that face is 1/6. So 100 minus 6 times, you will get that face up, right? So what does this mean? This exactly is exactly what Daniel asked the last time. When Daniel said that the ball falling down, that ball has an unequal, inhomogeneous distribution of mass, means in one side it is heavier, another side is lighter. Then what is the final distribution of the ball at the bottom it collected in the bin? That is exactly the same thing here. Here, when we play the dice, only one side we look at, that's 1/6. All other possibility is a 5/6, right? So that's similar to the inhomogeneous distribution of the mass. But if you do that for many times, increase the n number many times, you will get a Gaussian distribution. The only difference is this Gaussian distribution is not symmetric to the 0 point, to the origin. It has a shift, but it is still a Gaussian distribution. That is the point, right? So that's a very useful principle. Now, if we have the probability to be equally distributed, only two probability, okay? So then it is very like playing a coin, right? Only you have front side and the front face and the back face, right? So then P and Q equal, they both equal to 1/2, and then we only select the one face, like P, the front face, okay? The either the icon or the number, right? So in this case, we can still put this PQ into the same binomial distribution equation, and then if we play it 6 times, then you will see because this equal distribution for both sides, then we have a symmetric distribution of the final probability distribution, right? Now, if we increase this number n to very large, 100, then we also get a Gaussian distribution. As we add more and more number, this is more and more like a Gaussian distribution, and the distribution become increasingly smooth, okay? And then this one is symmetric instead of asymmetric, right? The previous one, previous one is not asymmetric. It's just a shift. It's just shift, not in the center point. But here, then you have 50% plus minus 50%, right? Previous one, because it's 1/6 versus 5/6, then it's more towards the smaller region, right? The lower region, right? Now, this explains that in the Galton board, when we put the ball in from the top, it keeps doing the same toss the coin again. This game happens again and again. Each time is a step, okay? The ball choose left or right, right? Equal amount. And then after many times of choosing, they finally appear a normal distribution, right? It's the same thing as here, right? So we have derived the mathematical language to describe this process, right? So let's take a look at this video one more time. It's very, very interesting. So the ball will come in from the top. Excellent. 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 That's the final one. Final one. This one is the Gaussian distribution. So this distribution, actually, we can think about it in two different ways. In the physics, is the people usually use both way. Either way is actually equivalent. One way is you have one ball. Another way is you have many balls. The first way, first method, first angle to look at this, you have one ball, you let it go from top, and then it will make a selection. And then you do it many times, same ball. It will not, every time you put it in, every step is random process. So then you repeat one ball many times. Each time they collect it into it, when the ball is collected into one bin, you make a marker there. Okay. And then finally you count the number of the times that the same ball be collected in the different bins. And then if you draw on the curve, you will get a Gaussian distribution. That's one way for each one. Okay, so that is similar to a Brownian motion of one particle. Another way is exactly what the experiment is going on here. You have many of these particles, and then you let them go through the top center part together, and all the balls are the same, and they will all follow the same statistical distribution, and then let it do it only one time, and then see how all of them distribute at the bottom of the device, right? So one time, one particle for many times actually is equivalent to many particles for only one time. Okay, they all appear, all demonstrate the normal distribution. Okay? So this is actually you can think in both ways. Now, this distribution actually can be mathematically expressed. This distribution actually can be written as 1 over sigma square root of 2n pi times exponential minus xn square divided by 2n sigma square. Okay, this is a very useful way to write. So this sigma is a standard deviation. Okay, is the square root of variance. N is the number of the times, number of steps, number of random walk steps. Pi is 3.14 minus xn square. This xn, this is actually a final position. Okay, divided by 2n sigma square. N is the number, same value. Sigma square is variance. Okay, so by knowing this, by knowing the characteristics, the value of that distribution, then we can write it into this form. This form is a Gaussian distribution. And also here, because we already know that the diffusion equation x square MSD equals to n sigma square, right? And then equals to 2 dt. And then you can put it in. Then this value equals to, then we put the time in now. Time and n is related, right? So then we have 1 over 2 square root of pi dt, e times minus x squared divided by 4 dt. Now is the only thing change here. Only thing changing here is the t. Okay, t. And this at a small t, if t is very small, you will find the distribution actually is more steep. And then as the t increase, this distribution now start to flatten down. the second t actually is equal to this. Okay, so you see t0, here, the first one is actually, if you do the simulation in the homework, you actually have a, you will practice that. If we have smaller steps, like 10,000 steps, then we get this steeper distribution. If you let it go more, 4,000 or 40,000 steps, then you get the more broad, but it becomes the lower. The area covered by those slope all equal to 1, right? And then you give it 160,000 steps, then it becomes even shallower. So by changing the step size, step number means change this t, we can get a different distribution of Gaussian distribution. Okay, and this process is actually as similar to one example. Actually can be seen in many different nature phenomena. One phenomena is if we have a ink droplet in the water, you dip one ink droplet into the water, then initially you will have a ball, right? Very dark ball in the water. And then all the particles of the ink, molecule of the ink, they actually start to diffuse now. Because the water molecule is bumping to it. Then they can start to diffuse. And then they take many random steps. Then you can see the ink become dimmer and dimmer, but the size become bigger and bigger because they diffuse around. So this is actually the same thing that can be mathematically described. This the steep one is actually the darker ink droplet at the beginning, and then the lower one, the flattened one, actually the wider one, flattened one, they actually can be used to describe when the ink size become larger, and then the density become less and less. Okay, so this is a very useful mathematical way to describe the random nature phenomena. And then in the previous one, actually we put the Gaussian distribution in a symmetrical way towards the origin. If they are not symmetric, if they are not in the origin, they are still symmetric. But if you shift it, you have a mean value here, non-zero mean value. Then in the Gaussian distribution, actually we have it include the non-zero mean value. So it's in here is actually x minus mu. Okay, x minus mu squared. So this actually is very useful. This formula, you should memorize it. It is very useful. It happens again and again in when you do the calculation. Minus the x minus mu squared divided by 2 sigma squared. Okay, 2 sigma squared. The unit is the same in the denominator and the numerator. They're the same. They are all length squared. Okay, length squared. That means length squared. That means positive length and negative length, they are the same. So this function, overall this function is symmetric with respect to the mean value, to the mu. Okay, and then here, this actually we showed before. At a one-time variance, one-time variance or one-time standard deviation, it covers positive and negative. You will cover 68.2% of the area. Two times standard deviation, you get an additional 27.2%. Okay, so overall we get 95.4% with 2 standard deviation. 3 standard deviation, we get 99.7% of all the area. There are still some in the tail, but they are much smaller than the major part covered by 3 standard deviation. Right. So that's the characteristics of normal distribution, Gaussian distribution. And here, when I write the value here, you can also calculate the A. You can normalize it. By normalizing this function, you can get the A, such as we know P equal to this guy, P equal to this, and then you do the normalization by doing the integration of dx, right? And then finally that is equal to 1, right? So this I showed it. I put the derivation here. So this is how you calculate it. Then you can from here you can calculate it. Yeah, the people usually, because this is only one integral, to do it it's better use two integral, and then the final result you can take the square root, And then the reason you do two integral, you put it dx1, dx2, right? So two multiplied together, and then get a squared, right? So the two together, the reason is they are equivalent. And then one can be dx, one can be in the orthogonal direction, dy. If you have dx, dy, then you can also convert it into the circular coordinate. Then you have the r d theta times r. So this is the same thing. This equals to dx, dy, right? And then by doing that, we can actually manipulate the inside components and then use the existing mathematical results. Okay. So here, these results here, then you can this re minus r squared divided by something times dr. This actually give the results that half of that something. Okay. So then it actually is here that is 2 sigma squared. Then it's 2 pi times sigma squared. Then 2 pi sigma squared. Okay. So this is actually the way people do it to let it multiply one time more is actually want to use this relationship here. And then here 2 pi sigma squared, then it's equal to 1 over a squared. Then we can get a, right? We can get a. A is this value, and then put this a back to here, Then this distribution is normalized. Okay. So once it's normalized, then we can use it to calculate, to test it. Then, although we said we know the mean and the variance, then to prove that's true or not, you can actually calculate it. So with this probability distribution, we can put that multiply that with x and then do the integration. That will tell us what's the mean value of this distribution, right? So then we can put all the value, the explicit a in. So then we do the integration here. Here then I showed detailed derivation here. You can test it. It's true. Okay, it's very useful for mathematical calculation. So you can separate here by doing separation. Then one term get erased, and then another term left. This term, when we calculate it, actually equal to mu. So it tells us that mu in the exponential term, mu indeed equals to the mean value of this distribution. Okay. Same thing, we can calculate the variance. Variance is actually equals to x squared average divided minus mu squared, right? So x squared mean equals to x squared times probability distribution, and then do the integration, and then overall minus mu squared. This one mu squared can get in, okay, and then get in, and then you can rearrange the terms inside, and then separate it into two terms. One of the term also can be derived or can be erased. Why erased? It's because we can make the term inside make them to be the product of two functions. One is an odd function, one is an even function. And then the integration is actually from minus to positive. Then this equation become it has both odd number and even number, both even number and odd number. Then they are cancelled out. They are cancelled out after the integration. Okay, so this will simplify the calculation of the integration. So then this left term here can be rearranged, and then this term also can be calculated by doing the mathematics calculation. Then you can change the term, right? Change the term here. Then you can finally get to this term. And then this term can be resolved by scaling the variable there, and then we can get the final results. Those are all fundamental mathematics. So mathematics now. So then you can get the value of this one, and then this value sigma divided by square root of 2 pi times sigma times square root of 2 pi. Then you actually get a sigma square. So this sigma square equal to this one. This is the variance. So this proves that the equation we just derived, the mean and the variance inside indeed are meaning the mean and the variance. Okay, so this is excellent. Now, yeah, No, yeah, that's the explicit term. Not you have all the terms determined. Once we know the mean and the variance, we can directly write Gaussian distribution. Okay? So that's very useful. And then what this means is this the mean and the variance of final distribution. And we mentioned that this final distribution is generated by a series and large number of individual steps. That individual steps actually also has their own mean and variance, right? So then we can count that. For the individual one, if the individual step, if they have the mean mu1, okay, smaller, each step is a distribution. They have the mean mu1. They have a variance sigma 1 squared, okay? Then after n steps, we can rewrite the overall final Gaussian distribution in this way. So now you see that here 2 pi n sigma 1 squared. So what is this one? N sigma squared. N sigma 1 squared. What does that mean? This actually is what we derived in last time. This equals to final sigma squared, right? Final distribution sigma squared is proportional to the individual sigma 1 squared with the coefficient equal to n, right? So then here is 2 pi times n sigma 1 squared. And then in the sun here also. And then in the same time, the x minus mu, right? Mu, that's the mean of a final distribution. But that equals to all the individual distribution, individual steps, the mean added all together, then equal to n mu1, right? So this explanation, this expression shows us, links the individual step, number of the step, and final distribution, okay? Final distribution. So this equation actually is the core of a theory that is called a central limit theory. Means after so many times those small distributions summary, we finally get a final distribution that can be expressed in a Gaussian distribution, and that Gaussian distribution's parameters are linked to the individual steps mean and variance. Okay, so this is a hugely important theory. Although this theory is not very obvious, but it is correct. It's hugely important. Okay. Now, why I say this theory is hugely important? Why I see this is because that tells us finally, after many times of repeating, we get a Gaussian distribution. However, it doesn't care each single step what is their distribution. We only care each step's mean and variance, but we don't care what kind of distribution they are, right? They can be many kind of distribution. For example, they can be the core toss. This is the binomial distribution, right? Binomial distribution. They can also be drunk the step. They can be 1D, 2D, 3D. Also, it can be molecular motion. They can follow different distribution, right? Different distribution. And then also bacteria properties, right? These can be all different distribution. However, if we summarize them together for enough times, our final distribution becomes Gaussian. And then that Gaussian distribution, their mean and variance are proportional to the mean and the variance of each single step. Okay, and both of them and both the mean and the variance linearly increasing with the time, right? So this one is important, and this also means in the nature we will observe many Gaussian distribution, but we observe them, we still don't know what each single step that contribute to the Gaussian, what is their probability? We do not know. What is their probability distribution? We do not know. Okay, we still need to dig into that, find out their distribution. Okay? And also another thing we discussed is remember when I talk about that two-step problem, what's the distribution of a BB work for 2 steps? What's the distribution? And I said that that step after 2 steps is actually the convolution, right? So that each step's distribution convoluted with itself. Then the final results equals to the probability of that BB after 2 steps, right? And then if you take 3 steps, then you convolute it one more time. And then 4th step becomes also one more time. Then that means if this one is correct, that actually means if we have any function, okay, can be, you see here, many different function. Any function, if we convolute it for enough times, it will start to appear like a Gaussian distribution, right? So as we show here, the particle move in a random way. We do not know what each step that in each step in the particle, what's their property. We do not know. You can change the water, change the liquid, or change the viscosity, or you change the particles property. Okay, they have an inhomogeneous mass, or they have the different electrical properties. But if they repeat enough times in the same condition, then they will behave like this. The position of the particle, if this here is one particle, you take many videos as a function of time. Each time you find the position of that video of that particle, then we overlap all the picture together, make the background to be transparent, and then overlap all the picture of that particle, single particle together. We will get this pattern, and this pattern is the distribution of one particle. Take many different steps, and if we draw, based on the intensity, based on the density of particle, we draw the curve. We get a 2D Gaussian distribution. Okay, so that's the very important theory we discussed. Now in the next step, let me briefly give a mathematical proof to show that if we convolve a function for many times, then it will give the Gaussian distribution. And let me show that. So that will be the proof of this theory, of this central limit theory. Okay, we will do it in 3 steps. 3 steps. First step, we will connect the convolution with an important transformation calculation called Fourier transform. We will first connect these two. Okay, that will give us a very useful mathematical formula that is useful for us to understand or calculate convolution better. Okay, then we will take 2 more steps to prove the central limit theory. So first step is we know delta function. If we have a delta function, that delta has the variable x minus s1 minus s2. So if this one, remember in the last lecture at the beginning, I mentioned that a delta function can be written in the integral form, right? So then that integral form is 1 over 2 pi. Take the integral of eik and then variable minus variable of this guy minus variable of this guy. So then it's s1 plus s2 minus x and then times dk, right? So this is the mathematical expression for any delta function. Okay? Now, if we have this one, this term can be rewritten as 3 terms. So this exponential term can be written as eiks1, eiks2 times e minus ikx, right? And then times dk. So this integral has 3 terms. Now, remember, we said that after baby's 2 steps, we have the distribution of that baby in the distribution in the in the mathematical formula is the integral of ds1, integral of ds2. Within the integral, you have ws1, ws2 times delta x minus s1 plus s2, right? We have that derived in the previous lecture. And I mentioned that this delta function here is very useful. That tells us final step is restrained after 2 steps. This delta function tells us the final step, final position is related to 2 steps taken already, right? So we have this term. Now with this here inside you have this we have this function, delta function, and this delta function can be written in this way, right? Can be written in this way. So then and this term can be written in this way, right? Then this integral can be added into this P2 function, added here. Then we will have P2 equals to 1 over 2 pi, 3 integrals together. Now we have 3 integrals, ds1, ds2, w1, w, and then this 3 term coming from here, and then dk, right? 3 terms. Now these 3 terms can be regrouped based on their variable. One term is here, one term is here, 1 over 2 pi, e dk, okay, eikx. Another is this term, ds1, ws1, eiks1, because they all contain s1. Third term is all group all the s2 terms together, right? And we already said that this term, we actually did a calculation before, right? We put the delta in, we eliminate s2, only get it become s1 function. Then we find this term, this expression actually equal to w convolute with w. We did that, right? Now, when we did, this is the final results. Now, if we look into these 3 terms carefully, we will find the 2 integrals, the later 2, is the blue one. These 2 later integral, what does that mean? Is they actually means doing a Fourier transfer. This actually is a Fourier transfer of the function w. Here is doing the Fourier transfer of function ws1. Here is the second one. All everything is the same, just change the variable to s2. Here is also doing a Fourier transfer of w s2. So these 2 functions actually is doing the Fourier transfer because it's ik variable. It's doing times the exponential ikx. It's doing a Fourier transfer of w s1 and w s2. Okay, and then if you know what is the Fourier transfer, then reverse the exponential term is actually the inverse Fourier transfer. That actually is showing here, showing in the orange one. Here you have the integral for these 2 terms, and then have e to the power minus ikx dk. This actually is the inverse Fourier transfer of Fourier transfer of w times together. Okay, this is super important. Here we have 2 w function convoluted together. This red one, they actually equal to, we take the Fourier transfer of w first, because you have a xs1, right? Fourier transfer of w first, and then Fourier transfer of another one here, another term here, okay? Multiply them together. And then the final results, I do an inverse Fourier transfer. Then I get the convolution of these 2 functions. Okay, this is very useful. It shows, it actually tells us if we have 2 functions convoluted together, because convolution is very difficult to solve in terms of mathematics. Then if you want to solve this, we actually can take multiple steps. First step is take those function, those w function. We do the Fourier transfer for each one individually. And then we multiply these 2 blue Fourier transfer term together. Then lastly, for the final product, we do a inverse the Fourier transfer. Then it will give us the results of convolution. Because Fourier transfer is easy to do in the computer or in the hand. multiplication is also easy to do in the hand. Then it solves the problem of calculating any convoluted function, right? Okay. Yeah, final form is actually look like this. You may already seen this, but you have not. This has been taught in many mathematical classes, but the mathematical root has not been shown in many classes. Okay, so here we use that two steps probability to demonstrate that if you have two functions convoluted together, we can actually do the Fourier transfer of these two functions first, and then multiply them together, and then that will give the Fourier transfer of final product of convolution. To get that final product, we do a inverse Fourier transfer, and then we get that final product fx. That equals to the convolution of two functions together. These two functions can be the same or can be not the same. Okay, so this term actually equal to this term. Okay, here the cross means simply just the product, just multiply together. Okay, so that's a very important step first. Okay, now let's stop here. Let's we will record another lecture for the Wednesday's class.